Okay, in this video we will look at the implications of the fixed point that we were talking about last time. Okay, what kind of fixed point you have depends on the theory that you have. Okay, so let's begin with a quick summary of what we have done so far. So let me just write down the solution of Kalan-Zemanzik equation because that is what we are trying to analyze. Okay, so solution of equation, and that is the renormalized Green's function, the endpoint Green's function at scaled up momenta. I am writing GR instead of lambda because I am not saying anything specific to 5-4 theory. So just to be very clear about that, I have changed the notation slightly. So we have seen that you can relate the Green's function on the left hand side to the same Green's function without scaled up momenta, but the coupling constants replaced by running couplings and running mass, and the mass parameter mr replaced by m bar, the running mass. And gamma tilde. Okay, I'm not putting a phi this time so that it is it's more generic, but we will still keep thinking that it is related to the field phi. Okay, that's what we had, and again gamma tilde m is 1 plus gamma m, and gamma tilde phi is d phi tilde plus gamma phi. Okay, but now you have gamma I'm not writing gamma phi, so you'll have the canonical dimension of the appropriate field that you are looking at, and the corresponding this dimension, anomalous dimension. Okay, just a second. Okay, so that is what we have, and then last time we talked about fixed points. What's a fixed point? Fixed point is when you have beta tilde equal to 0. Okay, so the value of g bar, that is gc, some value of g bar gc for which beta tilde is 0, let's call it, here I should have written beta tilde gc. Okay, so g bar, when it takes the value gc, then beta tilde gc is 0. Okay, that's a fixed point, and you can have an ultraviolet fixed point. Okay, or you can have an infrared fixed point. And so here gc could be or could not be 0. Now if gc is 0, okay, meaning the the running coupling vanishes at the fixed point, then we have asymptotic freedom. Okay, and the theory is called asymptotically free. Okay, 5-4 theory is not asymptotically free. QCD is a asymptotically free theory. Okay, QCD is the theory of quarks and gluons, and it's based on SU3 group. Okay, but we are not going to talk about this in here. But this is an important theory because it describes strong interactions. Okay, and this is an asymptotically free theory. Okay, and that is why it becomes very it is easy to do calculations in easy meaning. You can do calculations in this theory at high energies, because at high energies things start behaving like free theory, as I was telling you earlier in the last video, right? Because here, if the coupling is very small, then the effective coupling is very small, then it is essentially a free theory. Okay, if it goes to 0. So let's look at the implications of this. So let's analyze this exponential factor. Let's see how it modifies this. What is the effect of having a fixed point on this exponential factor? Okay, so let's analyze that. So let us look at the exponential factor. Factor in the solution. Okay, so that exponential factor is e to this integral d0 to t dt prime n gamma tilde okay. So when the theory has a UV fixed point, ultraviolet fixed point, okay, at GC, that is G bar of T GR goes to GC, right? The running coupling goes to this value GC as T goes to infinity. So when you have really scaled up all the momenta by infinite amount, then the running coupling that you should use on the right hand side of the solution of Kalan-Zimanzik equation, there you should use GC. Okay, so we are looking at this theory looking at a theory with the ultraviolet fixed point at GC, and then let's analyze what this exponential factor becomes. Okay, let me give it a name. Let's call it capital A. So this exponential factor becomes integral 0 to t dt prime n. I am right now just writing gamma tilde as d plus, so earlier I used to write d phi tilde, but I am just writing d now. Okay, it's the canonical dimension of the corresponding field, but if you wish you can keep writing this here. Okay, but I'll just omit. So d plus gamma. Okay, so this is gamma tilde, right? D phi plus gamma phi, but I'm omitting the phi. And gamma function anomalous dimension is a function of g bar, and g bar is a function of TGR. Okay, so this is, I have not taken any limits, I have just rewritten the same thing. Instead of gamma tilde, I have written here. It will be good if I change this. Okay, instead of gamma tilde, I have written d plus gamma, that's all. Now let's do the following. I write it 0 to some value t naught plus t naught to t. So I've just split arbitrarily, and I'm assuming that t naught is some large value of t. Okay, t naught is some large number. Okay, because I'm interested in t going to infinity limit, so I'm just splitting that integral into two parts. Okay, and really not doing anything else. And here then you have dt prime n times d plus gamma. I've just omitted the arguments. So what does that give? So this integral 0 to t naught dt prime n times this, when you have done, it will be some constant. It will give you some constant plus this integral. Okay, in this integral, because I am taking t naught to be very large, and t also I am going to take to infinity. So in that case, in the integrand, I can write this as d is anyway constant, n is a constant, the gamma function depends on t, okay, through this g bar, but the g bar goes to gc. Okay, g bar goes to gc in the t going to infinity limit, but because I am saying that t naught is also very large, okay, then in this domain from t naught to t, g bar is effectively gc. Okay, so I'll just replace g bar by its value gc. Okay, and then you have n times d plus gamma of gc integrated over t prime. Okay, and that is going to give you just t. Okay, and putting the limit gives you t minus t naught. And that t naught times the other things, that's a constant, so that I can combine in this constant. Okay, so all the constants that you get are put in here, and you get n times d plus gamma of gc times t. Okay, and this is in t going to infinity limit. Okay, because I have used this fact that in this limit the g bar takes a value gc. Okay, and I have dropped the functional dependence and put it a constant, because I am saying in this region I can approximate the gamma by just gamma of gc. Okay, and whatever difference is comes from the constants. So E really behaves as n times d plus gamma gc times t. That is the dominant behavior. Okay, t, because t is going to be infinite now, so this is an infinite quantity in the t going to infinity limit, so I don't worry about the constant. Okay, so that is how that is not E. E is the exponent of this. I am just writing the integral here, so E is the exponent of this, exponential of this. So you get E to this thing. So this is the behavior for large t. So let's, using this, write down the Green's function in the large t limit. So g tilde n r e to the t pi are the external momenta. Here you see gr, not g bar. Gr mr mu is equal to g tilde n r pi gc. Okay, g bar has taken a value gc now. okay, because I am taking T to be very large. Then M bar times this exponential factor which we just found out. Okay, and this factor I can write as e to the t n d plus gamma at GC. Okay, you see, this is how the Green's function will scale with t or e to the t. Okay, so here it is scaling with e to the scaling as e to the t power n d plus gamma GC. Okay, so the canonical dimension d, okay, is I mean, if it was a free theory, okay, there were no interactions, then you would have just gotten e to the t power nd, okay, based on dimensional analysis only. Okay, now because you are close to a fixed point, because t is going to infinity, okay, that canonical dimension is now replaced by d plus gamma GC, this anomalous dimension at GC, okay, at the fixed point. So that's the behavior you have. So this is looking very much like a free theory, except for the fact that you have to modify the dimension and replace the canonical dimension by canonical dimension plus the anomalous dimension. Okay, that is how it behaves. The Green function behaves in the vicinity of the ultraviolet fixed point. Okay. Now, if theory is asymptotically free, then GC is 0, right? Then GC is 0. That is what it means by asymptotically free, meaning the running coupling. This is the value of the running coupling, right? This is the running coupling constant, and that running coupling constant is 0. Okay, that's the condition for asymptotically free theory. And because gamma of 0 is 0, right? Gamma again you obtain from all these Feynman diagrams, and if you put the couplings to be 0, the Feynman diagrams will give you 0. Okay, so that is why the gamma will be 0. All these corrections will be corrections coming from the Feynman diagrams will be 0. Okay, so except for, so z will be equal to 1 plus 0. So that is why you have 0 here. So if you put this gamma equal to 0 here, then this exponential factor becomes what? E to the t power nd. There is no gamma c, right? So for asymptotically free theory, and the factor and d. Okay, that is what you expect based on naive dimension analysis. Okay, so it is really behaving like a free theory in that limit. Okay, in this case for an asymptotically free theory. When you have an ultraviolet fixed point with GC equal to 0. Okay, now let us do this in more detail instead of directly putting this thing here. So here we just put a constant here. Okay, now we'll do it with a little bit more care, and we will see that there is a minor modification to this, and I'm going to utilize some information about the beta function. Okay, so I'm going to take some particular theory. I'll give you a beta function of that theory and how gamma function also looks like. Okay, these are corresponding to some theory, and then given that, I'll just figure out how this exponential factor behaves, right? That's what I will do. So let's look at an example. So suppose beta function is given by this, and this is not for 5-4 theory. Okay, so beta function is minus beta naught g bar cube plus higher order terms, and beta naught is positive, so that this overall thing, the beta tilde becomes negative. Okay, that is beta tilde is negative. So what happens if beta tilde is negative? Okay, it will flow towards the fixed point. Okay, and so this is near g bar equal to 0. Okay, so I keep only the lowest order terms here, and g bar square, suppose this is also given to you. Okay, I'm just taking out some results from another theory and giving to you. So this beta naught is the same thing here, it's a positive number, g square t. Okay, so this is the behavior of g bar, the running coupling constant, or the square of it, in t going to infinity limit. So you see, if t is infinity, this is going to 0, right? Because if t is infinite, this denominator becomes infinite and it goes to 0. So g bar will be 0. So that is a this is an asymptotically free theory. Okay, so this describes an asymptotically free theory. Okay, so sorry, I made a wrong remark. So I mean, this is not an extra assumption. This is you are going to get it from here. Okay, actually this is what I am about to show you. So let's quickly do that part. So let's see that this is what you get. So we have already written that, we have already done that integral, and we had written that t is dg bar over beta g bar, and you integrate from gr to g bar. And this is an expression I had shown you earlier that I had here, right? So I'm just writing this thing, instead of lambda I'm writing g, but it's the same expression. So t is equal to d of the running coupling divided by beta tilde. Okay, from lambda bar of 0, lambda r is just lambda r, to lambda bar. So that is what I have here. Okay, and then you substitute this thing that is given to you. Okay, this result. So this gives you from gr to g bar of t dg bar over minus beta naught g bar q. Okay, and integrating this gives you minus 1 over beta naught, that's this factor, and g bar power minus 2 So let me write it below, and then you also divide by -2, 1 over g bar square. So here this is with t prime. Okay, so you get g bar of t square after putting the upper and lower limits, 1 over g r square. Okay, and gr is a constant because mu is fixed. So what does that give you? So if you solve it, you get g bar of t square of this is equal to gr square 1 plus 2 beta naught gr square t. Okay, all I have done is multiplied this, so that gives you 1 over 2 beta naught. Okay, then you multiply on the left hand side, so it becomes 2 beta naught gr square t, because I am also multiplying the entire equation by gr square. So you get 2 beta naught gr square t on the left, and then you take 1 to the other side and take the inverse. Okay, so that is what you get, and this is what is the result I gave you here. Okay, so if beta function is given to you, okay, that you have calculated, in the argument of beta function, see, beta function you will get by doing the loop calculations. So you did calculation at some loop, okay, and there when you are drawing the diagrams, you will be putting g of r. Okay, you will not be putting gr, you will be putting g of r. So you do the calculation, get the beta function. Beta function, you remember, it has the derivatives of z with respect to g or lambda r. You get that expression, and in that expression of beta, which is in beta tilde, which is in terms of grs, you replace gr by g bar. Okay, you replace the fixed coupling constants at mu by the running coupling, and that is this expression. Okay, so if you had done the calculation, you would have gotten beta tilde of gr is equal to minus beta naught gr cube, and you are just replacing gr by the running coupling. Okay, and then we see that the running coupling behaves like this with t. Okay, and let us also, so that is an assumption I have made, that I am looking at such a theory in which beta function is negative and given by this, and also let the gamma function be gamma naught times g bar square, okay, near g bar equal to 0. Okay, that is the fixed point. So close to the fixed point, meaning g bar is very small, so I am dropping the higher order terms, and gamma function is gamma naught, some constant, times g bar square. Okay, so what is gamma of g bar then? Gamma of g bar is equal to gamma naught, and here g bar square, I will substitute this expression. So I get gr square over 1 plus 2 beta naught gr square t. Okay, this is in the large t limit because we are close to the fixed point. Okay, because we are dropping all these terms, so we are close to the fixed point. So what does the exponential factor become then? So the exponential factor becomes e to the 0 integral 0 to t dt prime n d plus gamma naught. So that was there, nd, and here it was gamma, and I am putting the expression of gamma that I have just now calculated here, right? It's gamma naught times this. So gamma of g bar I have to put here. So gamma naught times gr square 1 plus 2 beta naught gr square t prime. Okay. See, I have to do an integral over t prime, and that is why I have written made the dependence on t bar explicit. So because g bar has t dependence, right? Running coupling has dependence on time, dependence on t, and that is why we have written it like this here. Because GRs, they are fixed. You have chosen a value of mu, GRs are fixed, beta naught is a constant, and now you have an explicit dependence on t. Okay, that is why we have done this thing. So we have this this exponential factor now. Okay, so now we can evaluate this. That's easy. So so let's evaluate. So you can just define this to be some constant and do some change of variables, and then you will get n gamma naught over, so this is n gamma naught here over 2 beta naught. Okay. Do that integral and you'll get this times log of 1 plus 2 beta naught gr square t. Okay, that's what you are going to get after doing this. This integral, this is exponential of this. It is e to the this thing. Okay, which is same as exponential of log of okay, sorry, this is not correct. This is only this part. Let me write it here. So this is equal so this is equal to e to the n dt. So this one n d times this integral just gives you t. So this is this times exponential of this other part. Okay, n d times gamma naught this part. Now this is fine. Okay, this is just e to the n dt times so this I can put in the within the log, so this to the, let me write it down anyway. This is n gamma naught over 2 beta naught. Okay, so this is exponential, so I get e to the t, this thing I am writing e to the t power nd. That is what you had seen earlier. This is the factor you get from knife dimensional analysis. Okay, and then you see this is in the asymptotically free theory. Okay, the coupling has gone to 0, so it's almost like a free theory, but in a free theory you will expect just this factor, okay, multiplying the Green's function. But now you have additional p's coming because of these renormalization effects. And what is that? That is, so I'll just drop this one, right? There is no, I'm in t going to infinity limit, so I have been dropping all the constants, so I will drop this, because 1 plus 2 beta naught g r square t, where t is infinite, is same as 2 beta naught g r square t. Okay, in the t going to infinity limit. So that one I'm going to drop, and you have 2 beta naught gr square t power n gamma naught over 2 beta naught. Okay, this is coming from, this is the canonical behavior. Okay, and this is the additional piece you are getting because of these renormalization effects. Okay, so even when your theory is asymptotically free, you are not going to get the canonical behavior. You are almost going to get it because this is the dominant piece, right? This is the exponential of t. So this is the most this is the most dominant part, and then you have small variation attached to it of this form, and it is these effects which were observed in experiments. So in one of the assignments I had given you about deep inelastic scattering, some kinematics I had asked you to do, and in these deep inelastic scattering experiments, such scaling violations, so this is a scaling behavior which you are seeing based on free theory, the violations to that coming from this factor, they were seen in this deep inelastic scattering. Okay, so this is what leads to scaling violations in DIS, deep inelastic scattering. Okay, let me just say in words again what we have done here. So we have seen that if you have an ultraviolet fixed point, okay, at which the coupling constant is 0, and if you look at your Green's function in that limit, you would very naively expect that because the coupling constants are going to 0, the scaling with these the scaling of momenta, okay, would be visible as this e to the d power nd. Okay, they will just scale canonically according to the dimension of that object, that n times the dimension of each of the fields. Okay, that is what you will get. But you see that here, even in that case, even when the theory is almost behaving like a free theory, even in that case, because of renormalization effects, you see this beta naught and gamma naught, these are all coming from renormalization. Okay, because of the renormalization effects, there is a small variation with t compared to what you would predict based on just canonical dimensional analysis. Okay, and of course this has also been seen in experiments where you are looking at strong interactions. So in deep inelastic scattering, you are really looking at the strong interactions. Okay, so I think I will stop this course here, and let me just summarize, or let me just tell you what things I have not done. Actually, I have not done many things, but some of the things that could have been fit in this, but there is no time left, is I should have also talked about the renormalization beyond one loop. Okay, so we talked about renormalization only at one loop in 5-4 theory, and one can show that theory is renormalizable, meaning you can get finite answers up to any loop order in 5-4 theory. Okay, and there is a general procedure of doing that, and I will recommend you to look at the literature and see how that is done. Okay, and yeah, we have mostly covered what I had planned in this course, except for this one omission of showing renormalization beyond one loop. But more or less we covered everything. And these techniques which we have learned here in the simplest context of real scalar theory, 5-4 theory, they are applicable with very minor modifications to other cases. So when you are doing electrodynamics or quantum chromodynamics, okay, the same kind of things you will be doing there also. So we have learned the renormalization and renormalization group in the simplest setting, but there is not much difficulty except for some technical ones in studying gauge field theories and QCD and quantum electrodynamics. Okay, so wish you all the best for your exam, and hope this course was useful for you. Okay, see you. Bye bye then.